Swayam Prabha. Digital India. Educated India.
I think I want to discuss a couple of things. First is if A is not equal to A transpose. Let us say we have A as a 3 by 3 matrix. Just to explain the idea. So, you will have 3 eigenvalues and I want to consider the case where we can have a complex conjugate pair. So, one eigenvalue will be real and 2 will be complex conjugate. Okay. So, I have lambda 1, lambda 2 and lambda 3. There are 3 eigenvalues. Lambda 1 is real and lambda 2 is lambda 3 conjugate, because the characteristic equation will have only real coefficients. The complex eigenvalues will always occur as a complex conjugate pair. If A plus IB is an eigenvalue, A minus IB will be an eigenvalue. Okay. So, this is just to illustrate. Now, corresponding to this, you need to look at U1, U2, U3. What are these? These are the eigenvectors of A. Sorry, I need to put this on top. Are the eigenvectors of A, and V1, V2, V3 are the eigenvectors of A transpose. Now, we still have the biorthogonality condition, which means inner product of U1 with V2 is 0 if Ui with Vj, let me put it like that, Ui with Vj is 0 if I is not equal to j. Okay. This orthogonality condition will be satisfied. Only thing is, since we have complex eigenvectors, we have to work in the complex space. There is no question of eigenvalue here. So, now you need to have the inner product of u with v is defined as sigma u bar vi. In my case, it is 3. So, when I do inner product of U2 with V3, so inner product of U2 with V3 will be inner product of U2 bar I V3 I equals 1 through 3. The superscript is telling me the third eigenvector. This is the third eigenvector, this is the second eigenvector, this is the ith coordinate. So, since we are working in the space of complex eigenvalues, okay, we need to take the conjugate of the first guy, because that is how we defined inner product to ensure that the axioms are satisfied. Okay. So, this is the only difference. So, we have these 3 eigenvalues, these 3 eigenvectors, each of this is orthogonal to the eigenvector corresponding to the other eigenvalue, but the inner product has to be defined like this, because this the first guy is real, no problem, second guy will have complex elements. So, you need to take the complex conjugate and then do the inner product. Okay. That's clear? You can define it any way you want, but you have to be consistent throughout. You can define it as ui bar vj, you can define the inner product as ui bar vi or sigma ui vi bar. This is also fine. This is either one is fine, but if you decide on one thing, stick to it. because there I was considering only the real case. Inner product for the inner product is always with the complex conjugate only. No, no, sorry. Okay, understand what is understand what you're saying. Okay, so it is a complex conjugate of this. You are right. Sorry, yeah. So the orthogonality condition, the okay. What have I written here? I have written, yeah. So this was not the biorthogonality condition. This condition is wrong. Yeah, this condition is wrong. Yeah. So you are right. So this condition has to be, you have a complex conjugate one of them, and I think I complex conjugated this guy. Yeah, that's what you are saying. So the biorthogonality condition, thank you for correcting me. So I think the biorthogonality condition is the perpendicularity of the ith eigenvector with the complex conjugate of the jth vector. Yeah. And now, so let us not confuse the issue, let us say this is what it is. This is how I am defining my inner product. So now if I want to do this, I will have both. Okay? Yeah, I think I goofed up a bit. So here V3 bar, so the orthogonality is with V3 bar. So I am keeping V3 bar as it is, I am taking the complex conjugate of the first. So let me not confuse the issue with having this on the board. Let us stick to this. So again, this is the biorthogonality condition. You take ui and find the inner product with Vj bar. So the way the inner product is defined is by complex conjugating the first vector coordinates, because we are working in the complex space, and this inner product is, therefore this is not complex conjugated, this is as it is, and this is complex conjugated, you get this. Okay. This is generally valid, but if it's real also, then there is no question of taking complex conjugate. Yeah. We do not have to, because everything will be real. Complex conjugate of a real quantity will be itself. Yeah. Yeah, but this is the general thing. If it turns out all the three eigenvalues are real, if these three eigenvalues are real, then no complex conjugate is going to show up. Okay. Now I think the other question was, I think there is nothing wrong with what I have done just now. So now the question is, I have repeated eigenvalues. Okay. So let us say a particular eigenvalue, and let us, we are talking about the case where A is equal to A transpose, okay, and A equals A transpose. So a self-adjoint system. So point I am trying to make here is, we are guaranteed n eigenvectors. So if an eigenvalue is repeated r times, then we have r eigenvectors. Okay, and these are vectors can always be chosen to be orthogonal. Okay, and maybe orthonormal also. So rather than I talk about consider, I'll take the simplest case. Okay, A equals the identity matrix, which is, let us say, 3 by 3. Now lambda is 1 repeated 3 times, and if I want to find the eigenvectors, I can choose I can choose Ax equals x, because that's lambda x, or A minus Ix equals 0, which is basically, if I subtract 1 from all of this, I get 0, 0, 0. That's your thing. So now it looks like, so you can choose vectors, right? Anything is going to, your first eigenvector will have some 3 coordinates. Okay, you can choose it to be anything you want, because you are going to multiply 0, 0, 0. Okay, so you can choose u1 to be 1, 1, 1, for example. No, actually we should not do that, we just do 1, 0, 0. Let me not confuse you, just keep this as the eigenvector. Okay, now this is your first eigenvector. The second eigenvector u2 will be of the form, let us say, A, B, C. Okay, and I am going to choose this eigenvector so that it is perpendicular to the first one. So I have A plus B plus C equal to 0, right? B multiplied by C, A multiplied by 1. Okay, so what have I done? I am choosing u2 to be perpendicular to u1. So A multiplied by 1 plus this equal to 0, that means implies A is 0. So if A is 0, I am guaranteed it is perpendicular. Now I am free to choose B and C the way I want. Okay, and I have this option of choosing B and C, and I can choose anything I want. So I am going to choose my eigenvector u2 to be of the form 0, B and C, and what we do is 0 multiplied by 0. So there is an arbitrariness, because everything is 0. I can choose B, as long as my first element is 0, I am guaranteed orthogonality. B and C I can choose the way I want. Okay, so one choice is 0, 1, 0, because this guarantees orthogonality, and it also guarantees that this equation is satisfied, Ax equal to this. You can have some other choice if you want. Okay, now the third eigenvector you can choose to be orthogonal to the first and second, and to satisfy the equation. Okay, u3 with u1 must be 0, u3 with u2 must be 0. So u3 with u1 equal, and if u3 is of the form DEF, this implies D must be 0, E must be 0, because I chose u2 to be like that, okay, and this then F will be 1. Now my eigenvector has to be non-zero. So basically 0, 0, 1. So this is the reason when you have repeated eigenvalues, at least for a self-adjoint system, you are guaranteed that the geometric multiplicity is the same as algebraic multiplicity, which means if an eigenvalue is repeated r times, I have r eigenvectors, and you can choose the eigenvectors to be orthogonal, okay. What I have given you is one choice of orthogonal, okay. You could have chosen here 1 minus 1, that is also orthogonal, okay. Yeah, because b plus c must be b minus c is 0, yeah, it does not matter, but third one will be different. Anyway, now it looks like I want to solve. I am going to get my matrix where I get integers as eigenvalues. I'm thinking of a matrix now. I want to solve this problem, okay, subject to some initial conditions. X at t equal to 0 is 1 and 2, let us say, okay. So I am going to, so this is just a problem right now, and I mean I just remember my batch reactor problem from the previous class, so I think I am just going to use that and say A is of the form 4 minus 5 minus 4 5. Okay. So this is basically not a real symmetric matrix, but yeah, this is my matrix A. I want to basically solve this problem, and last time I was explaining to you that we are doing it in eigenbasis because I end up decoupling the equations, okay. So now I am going to basically use the same method and say that first find the eigenvalues and the eigenvectors. The eigenvalues of A are given by 4 minus lambda multiplied by 5 minus lambda minus 20 equals 0, okay, and this gives me lambda squared minus 9 lambda equals 0, or lambda equals 0 and 9. Actually, I made a mistake here. You know what the mistake is? I'll tell you what the mistake is at the end, okay. What's the mistake? Anybody? Rows are dependent, there is nothing wrong with that. In a real problem, this will be minus, this will be plus, this will be plus, this will be minus, okay. But let us proceed with this. In the actual problem, if you see yesterday, this will be minus and this will be plus, and this will be plus and this will be minus. I just did the opposite. But let us see what happens as you go along, so that you understand that when you make a mistake, somewhere things are going to go wrong, okay. But I know that this is wrong, but let us proceed. So now, corresponding to lambda equal to 0, I am saying the first eigenvalue is 0, lambda 1 is 0, okay. What is the eigenvector? 4 x1 minus 5 x2 equal to 0. It is the same thing because the 2 by 2 system, I'm not going to write it again, okay. And I can choose x1 to be 5, x2 will be 4. So u1 will be of the form x1 is 5, x2 is 4. So, I do not have to worry about fractions and all that. If I choose 1, then I have to worry about 4 by 5 and 5 by 4. Okay. So, this is an eigenvector corresponding to lambda 2 equals 9. I have minus 5 x1 minus 5 x2 equal to 0, right, minus 5 x1 minus 5 x2 equal to 0. So, x1 plus x2 is 1. So, u2 will be of the form, what do you want to 1 minus 1, minus 1 1, 1 minus 1, okay, good. You can choose either way, okay. Remember, if 1 minus 1 is an eigenvector, minus 1 1 is an eigenvector, minus 5 4 is also eigenvector, 20 16 is also eigenvector, okay. Eigenvector is not obtained uniquely, any scalar multiple is a eigenvector. I need to similarly find for the transpose, okay. So, now for A equals A transpose 0, I have 4 x2 equal to 0. So, I have 1 1 as the eigenvector, and corresponding to lambda equal to 9, minus 5 x1, you know, do the transpose, okay. So, now this is V1 and V2 will be, when the x1 is 4, x2 will be minus 5. Now, just to check if what we have obtained, so this is clear how to find the eigenvalues and eigenvectors. Now, just to check if what I have got so far is right, check the bi-orthogonality. U1 with V1 is of course not 0, but U1 with V2 is 0 and U2 with V1 is 0, inner product of U2 with V1 is 0, okay, yeah. So, so far so good, most probably you are right, on the right track. The other thing is, there is a theorem which says that the trace of the matrix is equal to the sum of the eigenvalues. So, my eigenvalues were 0 and 9, 9 plus 0, that is the same as the trace, okay. That is one more check you can make, and you can look at the determinant of this is 0, that is the product of the eigenvalues, that is 0. So, I mean, these are small cross checks you can make to make sure you are proceeding properly, okay. So, I have gotten the eigenvalues and the eigenvectors, and my solution x of t is going to be of the form Ci of 0 e power lambda I t ui, okay, which is written as C1 0, lambda 1 is 0, so that goes off u1 plus C2 0 e power 9t u2, that is my solution, okay. This is C1 of 0, what is u1? 5 4, and C2 of 0 is 90, 1 minus 1, 1 minus 1, Now, this particular thing is going to satisfy the differential equation, okay, but it does not satisfy the initial condition which I have. So, I find the C1 0 and C2 0 so that this initial condition is satisfied. Okay, you can substitute this back inside, you will see that this satisfies the differential equation. Okay, but now this is still unknown. Only if I find out C1 0, C2 0, I can tell you what the solution is. Okay, so how do I find out C1 0? I need to take the inner product of this with one of these guys. If I take the inner product of this with V1, okay, take the inner so this is x of t at time t equal to 0 is 1 2. Okay, this has to be satisfied. So again, these are basically two equations and two unknowns. The two unknowns are C1 and C2. You can solve it, but what we are going to do is we are going to find out by doing the inner product. Take the inner product of both sides with the eigenvector V1. Okay. So, we take the inner product of this with V1, which is 1 1, C1 of 0, 5 4 1 1, let me put a proper inner product sign. Okay, this is 0. Yep. Yeah, thank you. I was wondering. Yeah, this becomes 1. Yeah, thank you. Because this is evaluated at time t equal to 0. Yeah. Yeah, thank you. So, what is C1 of 0? Equals 1 plus 2 is 3 divided by 9 is 3 divided by 9, which is 1 by 3. Okay. I just took the inner product and I have used the biorthogonality property. So, that goes off, but I am taking the inner product of the, you should take, like she said, the inner product of the complex conjugate of this, but this is real. So, no complex conjugate problem now. To find C2, take the inner product with V2. Actually V2 bar, which is the same as V2. So, I have inner product of 1 2 with 4 and minus 5, this is equal to C1 0 inner product of 5 4 4 minus 5 plus C2 of 0 times 1 minus 1 comma 4 minus 5. Okay. So, this gives me 4 and minus 10. So, minus 6. Minus 6 divided by 4 and 5, 9. And this goes to 0 because of biorthogonality. Okay. So, basically I found out C2 of 0 to be minus 2/3. So, now I just have to substitute this here. So, the actual solution is x of t equals C1 of 0, which is 1/3, times u1, which are very beautiful. Oh, good, I don't erase it. 5/4. C2 of 0 is minus 2/3, e power 90, 1 minus 1. Is it? Yeah. So basically, now I can. This means the first element x1 of t is 5/3 plus or minus 2/3 e power 90, and the second variable, because this is actually a system of two equations and two unknowns x1, x2, right. I want to find out individually how each of them is varying. One can be concentration, one can be temperature. x2 of t is 4/3 plus 2/3 e power 90. Of course, after you get the solution, you have to check if it satisfies the differential equations and the initial conditions. Initial condition is easy to check. Put t equal to 0, you get 1. Put t equal to 0, you get 2. So that's good. Initial condition is satisfied, okay, because the first one is 1, second one is 2. You have to differentiate this and substitute back inside. You will see it satisfies the equation also. So this is the mathematical method of how you go about solving. I told you there was a mistake in the problem. I mean, especially if you are talking about the equations representing the concentration in a batch reactor. What is the mistake? As time goes to infinity, as t goes to infinity, what is happening to the solution? As t goes to infinity, what happens to x1 of t? It also goes to infinity. Okay? x2 of t, go to minus infinity. x2 of t is going to plus infinity. So this will be great, no? I mean, if you have a reactor where you have infinite amount of products formed, infinite amount of this thing formed, you don't have to do anything. You just have to sit, put your foot on the table. Batch reactor is going to give infinite amount of product, it will make a lot of money. Yeah. So what does that mean? That means something is wrong in the equation. So the point is, I need to get a minus 9. Then that will go to 0. So because I had interchanged the signs, okay, I am having this issue. So the point is, you people, I am sure when you are doing your research, when sometimes you will make a mistake in the sign, sometimes something will go wrong, your equations will be either giving you results. So when you get a result, you can get a wrong result, but it's better for you to know it is wrong than for somebody else from outside to come and tell you it's wrong, right. It is better that you find that something is wrong. So that's the point here. So the point is, where is the mistake? The mistake is the very first equation that I wrote, okay. And so basically this is physically not possible, because my matrix A should have been, so my matrix A had the issue. Can you tell me what the matrix was? A? Some 4 minus 4 plus 5. Just to explain why this sign is incorrect. So Supposing you have A giving B, CA dot, which was, let us say, x1 dot is K1 and K2 minus K1 CA plus K2 CB. So, this is minus K1 x1 plus K2 x2, assuming CA is x1 and CB is x2, and similarly CB dot, which is x2 dot, is plus K1 CA minus K2 CB, which is K1 x1. What am I doing wrong? Yeah, this is minus here, minus K2 x2. See, from the physical point of view, if you are a chemical engineer, a scientist, A, because the first order reaction, the forward reaction is getting consumed, it is minus and is produced by the second. So, the first element, the A here should be positive, negative, positive, positive, negative, negative, positive, positive, negative, because it is getting consumed by the forward reaction, there is a minus sign. But what I had done was I not taking that into account. Okay. So, I was saying A is getting produced proportional to A. So, basically the mass balance was getting into a problem. If you are just doing an exercise in mathematics, it does not matter because you are solving ODEs, but if you are solving a problem in engineering where these variables have physical significance, then you will get into some ridiculous result. Okay. So, I mean it is good that you make mistakes sometimes because you learn from the mistakes. Okay. So, that is something you need to be careful about. This is your ODE example. Okay. What else? PD example. That is for the next quiz. Okay. But yeah, I wanted a non-self-adjoint system because I wanted to explain the bi-orthogonality. Anything else? I don't. So, basically what we will do is we will start partial differential equations. Okay. So, we just whatever we have done is ODEs, and what we have done so far is what I call finite dimensional systems, where you only have a finite number of variables you are solving for, x1, x2, x3. So, we are going to go from finite dimensional systems to infinite dimensional systems, which basically means partial differential equations. Again, these are things you have seen, but because of this framework that we have established, metrics, norms, same things we are going to use there. We will extend all these concepts to partial differential equations. We will again talk about operators, we will again talk about self-adjoint operators, same business of properties of eigen values and eigen functions, orthogonality, bi-orthogonality, everything is going to come, and then we will use that for solving PDEs. Okay. So, exactly whatever we have done here, we are going to extend it there. Thank you.